So I wish to express my appreciation for the opportunity of my presentation, especially for the organizer, Professor Kyungkeun Kim. And yeah, I mean, after finishing my PhD, it was a great opportunity, I mean, to learn about some mathematical problems related to biology. So actually the studying problems when I was in the Max Planck Institute, I was under the groups of Stefan Müller's, but there were some professors under his group. So one of our professors is the Angela Stevens. I met her that time, 2002 and 2003, and then originally I studied in Navier-Stokes and fluid equations, but I realized that the Keller-Ziegler equation is also one of the interesting equations. But that time, actually together with the Professor Hyung-Joo Hwang, actually Angela suggests some papers written by some French groups. I think the Passams, Sumaiza. I mean the relation between the kinetic equations and the continuum equation. So from the kinetic equation, can we derive the continuum equation, Keller-Ziegler, classical Keller-Ziegler equation, and so on and so on. So actually that was originally done by the French groups, but we realized that actually already the Hillens gave a lot of talks about the structure of the Turing kernels on. But when you read the paper, somehow the structure of the Turing kernels actually implies the derivations of continuum equation, but we slightly improved their results because the paper's dependence on the Turing kernels only on the density of the chemicals. But typically people says that, I mean, it is said that depends on the gradient of the chemicals or maybe temporal variations of the chemicals. And so, but we didn't succeed the improving the dependence on the temporal variation, but at least the spatial variation is okay. So we include the dependence of the gradient of the Turing kernels, and still the kinetic equation has a global existence of solution, and then we also derive the the short time connection between Keller-Ziegler equation and classical Keller-Ziegler equation. So that's the starting point. Later that I also had a great chance to work with Juan Velasquez, who is now the professor in the applied mathematics department in the Bonn University, I think. So he is also expert in the kinetic theories, and as far as I understand, when it comes to kinetic models, the structure of the Turing kernels is important. So we study another types of problems related to the alignment of the actin filaments. It's a bit kinetic models, but we start with the OD types of equation, but it's written in terms of integration, which has some structure of the Turing kernels. And so that's the starting point. Still, we have some joint work, but this is the recent work with Angela Stevens. Now the Angela Stevens in the University of Münster in Germany. I mean, she was in the Max Planck, and then she moved to the Heidelberg. Eventually, she now currently is in the full professors in the Münster University. So this work was done, quite recent work, but maybe it was studied 1 year ago. So the title of my talk is the Blowup and Global Existence for the chemotaxis-growth system. By the way, I'm not great at mathematical biology. I mean, I think the mathematical biology is quite wide. So, in particular, there are many models, but I'm not interested in I'm not good at modeling, but I'm interested in kind of existence matters or regularity matters of the models related to the biology problems, mathematical biology problems. Okay, so the plan of my talk is as follows. So let me first introduce the models and give some motivation of the study for the problem, and review some known results, and then state the main result and give the sketch of the proof. Maybe I'm trying to avoid the technical parts. Only maybe I'm give the mainstream how the proof goes of the problem. Okay. I think that most of you now may be familiar with this model, maybe not. But just in case, let me remind you the classical so-called Keller-Ziegler equation, which was suggested by the Petrlag and Keller-Ziegler. Probably you will see the cartoons of the motivations of this equation. But so U is basically indicate the density of the biological cell, biological organism. In fact, I think as far as I understand, it is modeled by the biological phenomena related to the certain amoeba, which is called Dictyostelium discoideum. So in fact, this kind of biological organism, in some situation, they produce the chemicals. So they show some aggregation effect. So this model is the some possible plausible models which may describe the such kind of behavior. I mean phenomena. So U indicate, as I said, is the cell density, biological cell density, and then V indicates here. V indicates the chemical attractant. So this part is basically shows some aggregation effect, and the other thing, I mean, the second equation is kind of linear, but this non-linearity is quite severe. So I think even in 2D case, the classical model shows up loss of infinite time. So, if you consider the boundary domain case, then typically no flux boundary conditions are assigned, which means somehow the total mass is preserved for U because of these boundary conditions. Okay, in 1D case, solutions globally exist in time. However, even in 2Ds, if the initial mass of U is beyond the critical mass, in this case, I think 8 pi divided by chi or something like that. So total mass is important when it comes to the matter of the global existence or loss of infinite time. So more precisely, in the case, the first result regarding this Blowup result is done by Jägers and Luckhaus. By the way, Professor Luckhaus is the husband of the Professor Angela Stevens. Okay. Anyway, they show that the loss of infinite time in 2D when the equation is the parabolic elliptic types. So in other words, the phi of t doesn't appear in the left-hand side. It's kind of a approximation of this system because actually what I heard that the chemical equation is the diffusion process is much faster, so almost like the elliptic types. I mean, so that's why you can remove the time variations. So not exactly same equation, but in a way, it's good approximations of these models. Anyway, in this case, they show that blows up in a finite time of these models, as long as the initial mass is large. Okay, and also time parabolic case is also treated by the Herrero and Velasquez later, but the result is more or less same. As far as remember, they show that blows of infinite time in the disk in 2D case, but anyway. So typical behavior is as long as the initial mass is large, then you can show that the flows of infinite time. Flows means actually the direct delta formations occurs in a finite time in 2D case. In higher Ds are slightly different. I saw some papers. There are different types of blow-up, like self-similar types of blow-up in higher D, 3D or higher D, and also direct delta types blows up occurs. But as far as I know, in 2D case, always blows up occurs as the form of the direct delta, sum of the direct delta, depending on the initial mass. Okay. Okay, this is a kind of cartoons of the dictyostelium discodium, which is the certain types of amebo. So most of you maybe already know about this thing, but quickly let me briefly explain the life cycle of dictyostelium discodium. So they have 4 different types of status. So vegetations, okay, which is the status when the food is enough. Then basically the distributions of the dictyostelium is uniform, no reason to aggregate. But in case there is no sufficient food, then they produce some chemicals and they show some aggregation effect. So the next stage is the aggregation status. They form some mounds and migrate, move to other directions. That's the status, the migration status. They form some fingers. Okay, this is still maybe migration status. They form the slugs and move to the other spaces. And then eventually they form different types of cell. So they make some fingers like this form. So the top becomes spores, then the bottom becomes stalks. So what is observed is that there are 2 types of different cells. So the upper cells become spores. The other types of cell forms the stalks. Eventually, these stalks just die, and then these spores spread. So, and then repeat this cycle again and again. So this is observed in the lab, even in the lab, within 24 hours. Okay. So the interesting thing is, I think the Keller-Ziegler equation somehow the models describing this status from the vegetative status to aggregation status. Okay. So let me show one other pictures. Okay, this thing is observed in the experiments. So here, they kind of form some mound or something like that, and then eating this during this process, they actually what is observed, they produce some chemicals, CChem. So it's CChem, and then the patterns are maybe more than the Keller-Ziegler equation, but anyway. So Keller-Ziegler is somehow understood as one of the possible models describing this behavior. Okay, so mathematically, many mathematicians study these types of equations, and then still, I think it's. Yeah, okay. I mean, still there are many open problems, and then there are many different types of models now developed. Okay, so. The model we are interested in these types of models. So this exactly same as the Keller-Ziegler type, but there we also take into account effect of the growth and death of the biological cell. Simply speaking, F is like the form of this. In other words, logistic terms. The one different thing is even if you have a no flux condition, if we add this, then we don't have any more mass conservations. So maybe the mass decreases because of this effect. Okay. So maybe that's the good thing for the regularity methods. Okay, because a priori we have only the mass conservation. That's all. We don't have any weak solution. Typically, we don't have that. And so usually we have a local existence of the solution in time, but maybe these guys basically would be useful for proving global existence of solution, but not so much. Okay, depends on maybe dimensions or but okay. Let me give the more precise known result for regarding this issue. But the equation we are really interested in these types of equations. So there is no diffusions. So only the reaction terms are there, and then we add these logistic terms, and then the second equation is again the elliptic types of this. Okay. Okay. So the difficulty is actually a existence of this solution, even in local in time. Why? Because we don't have any these diffusion terms. Then, in a way, you could say the first equation could say hyperbolic types, not anymore. I mean, not the parabolic type anymore. So then, actually, the existence of the solution is not obvious because we have to somehow specify which spaces are you looking for the solution of this. So this is one of the difficult part, I think. Anyway, okay. Suppose there is a solutions. Okay, maybe classical solution in a short time. Then, what can you say about this? Still, we can ask such kind of questions. What types of questions? Actual regularity questions. Blowup in a finite time or global existence of time. Okay. The motivation of study, actually, we found that some paper written by the Winkler, who is I think currently is in the Paderborn in Germany. And he wrote a paper regarding these problems in 1D case. So why is it 1D? Because one of the difficulty when it comes to existence matter of these equations is that the second equation actually is a linear equation. So this equation is quite complicated, but this structure may help to prove the existence of solution. But what is the good things for the 1D? The 1D case, actually the second derivative of v is nothing but just u minus v. 1D case, because 1D means if you have one spatial dimensions, then Laplacian means just a second derivative. So we have a control of the full second derivative in terms of u and v. But in higher dimensions, it's a bit slightly different because we only have a Laplacian, control of Laplacian, not the full second derivative. That's the main difficulty when it comes to establishing the solution local in time. Okay, I mean, we carefully read his paper and then we realized that that is the one difficulties in these problems in higher dimensions. Not only this, there are some several, but I think that that's the most of the difficult part of this problem. So the Winkler's, he proved the only 1D, but we realized that because this is almost like a second derivative, but slightly we lose some the kind of mixed derivative, but there may be some way to overcome such kind of difficulties. Okay, so then eventually we succeed. I mean, actually, to be honest, as I said, I studied some the fluid equations, and then there are many tools developed to control the second derivative in terms of the estimate. That actually that works in this case. So, so it's quite interesting. You'll see it clearly later. Anyway, so maybe we can consider more general types of logistic terms, like the special case is beta is 1, which is a previous case, but you also consider the more general case where the beta is slightly better than the linear, which means beta is positive. So you may expect that if the beta is bigger than 1, then solution globally exists. Actually, this is the case, as you expect, and beta is less than 1, then solution may develop singularity. Actually, this is a yes. A priori, yes, but also, then what happens in the case beta is 2? Then depends on, actually, it turns out in such case, did I miss the previous result? Okay, I didn't. Okay. In the case of beta is 2, both cases are possible. what I mean is Blowup also possible, global existence is possible, but that kind of things depends on the size of this parameter mu. But it's not so complicated. I mean, in a way, it's obvious. Actually, what is done? Yes.
Question. So
yeah.
the hyperbolic case 2, does this depend on space dimension? So are you now 2D, or is this any space dimension?
Any space dimensions. Any space dimensions. Yes. Yeah. In this case, doesn't depend on. I mean, I think the structure is more or less same. I think the yeah. So you'll see more clearly later. So it's for any dimension is fine. And also, finally, the last result in this talk is about the parabolic elliptic case. So, which means the Laplacians are now there. Then, at least the local existence is easy. What is known is in 2D case, for these models, all solutions are global, which was, I think, done by the Japanese groups, Osaki and et al. For any mu. So as long as mu is positive, then solution globally exists in time for these types of parabolic elliptic case. I think the even parabolic case is also true, but then the mu is maybe large, but I don't know. They specify the specific values of mu, but at least for the parabolic elliptic case, for any mu, but if it's positive, then actually solutions are global. That's the 2D case. Later, Tello and Winkler proved that these models in higher dimensions, more than 2, they proved that if the mu is bigger than these numbers, n minus 2 divided by n, then actually also solutions are global. And so, because somehow these models also relate to our models under our consideration, only difference is these Laplacians are there or not. And then we also read their paper and we realized that the limiting case, I would say, limiting means mu is exactly the same as n minus 2 divided by n. And if it's less than this, which is something like a supercritical case. I have no idea for such case, but limiting case, maybe we can show that the global existence for these models. Actually, that's the case. So we also prove that we cover the one limiting case, namely in any dimensions, if mu is exactly the same as the n minus divided by n, then still the solution globally exists. Okay, that's the last part of my talk today. Okay. So let me summarize the main result. Okay, the Winkler's case, he did this global existence of Blowup of infinite time. In case the bounded domain, so basically the domain under its consideration is just intervals. But our case, not only the bounded domain, but also whole space is okay too. But one restriction we realized, after submitting paper, actually we got the reference comments about the kind of regularity of the domain. In fact, what is needed, it's maybe technical points, but the convexity of the domain is necessary for our model. That's quite interesting. But my guess is maybe we don't need it. But when it comes to because we have to construct solutions independent of such kind of construction, then we take the limiting process. From that process, actually we need the convexity. But a priori, we don't need it. So it's a bit strange to me at the beginning, because when you have a priori estimate, then usually somehow the approximations always works. But this convexity is needed for the process of approximation. So we cannot remove such assumptions. Okay, that's the one thing I have to address. Okay, you'll see more clearly later. Okay, so in this case, mu is positive. There are two alternatives. In other words, do you remember what is the mu? Mu is the parameters in front of u square for the logistic terms. So if mu is bigger than 1, then T0 infinity. So what is the T0? We have a local existence of solution in this class. We construct solutions of the hyperbolic elliptic models. That are also not easy parts. Okay. So the first part of this theorem is that there are some time T naught, so that we have some solutions of the models, hyperbolic elliptic models in this class, which is this seems like not the classical sense. Actually, it looks like a weak sense, but I think the bootstrapping argument works actually before time T0, solutions becomes classical. Okay, but I just write this class, but that's enough for our purpose. Anyway, this is the existence of the solution locally in time, and now the question is whether or not solutions are globals or Blows of infinite time, which means if T0 is finite or infinite. That's the question, right? Okay. So the first result, if mu is bigger or equal to 1, then T0 is infinite. So solutions are global. Okay, in this case. Okay, there are certain classification in the case Rn or bounded domain, but this is crucial assumptions. And the other case is, what if mu is less than 1? Then, if the initial data is sufficiently large for P is depending on mu, then actually it shows up, blows up in a finite time. Okay, that's the classifications. And similarly, okay, this is more general types of hyperbolic elliptic equations. Then now, as I said, so beta now, the previous results, actually the global existence of Blowup depends on the size of the parameter mu. However, in this case, the mu is not important. Actually, the power of beta is important. So if beta is bigger than 1, then solutions are global. Actually, this somehow, the minus sign means the, I think the subcritical case compared to the aggregation effect. You'll see more later, clearly later. But beta, as long as beta is bigger than 1, then actually this guys win this aggregation effect. So this is subcritical case. Doesn't depend on the values of mu. And beta is less than 1, then this is a supercritical case. So the result is the same as the previous case in case mu is less than 1. So that if initial data is sufficiently large in the LP class for any P, then actually it shows Blows of infinite time. Okay. Finally, as I said before, this is parabolic elliptic types of equations, and as I said, we only treated the limiting case because the subcritical case already treated by the Talloes and Winkler 2010. And so the main result is that okay, so even if the mu is the same as these numbers, critical numbers, then still we have a global existence in the whole space, so bounded domain. In this case, we don't need the convexity, by the way. Only the convexity is required for the hyperbolic elliptic types equation. Okay. Okay. So let me give some just the main idea how the proof goes. Okay. So we when it comes to constructions of the solutions locally in time, then we have to approximate. We add Laplacian with this parameter epsilon, and then actually we wish to have we will have a estimate independent of epsilon. So the patching to the limit, and then the solutions like this, and then also we show that the uniqueness in that class, and so on and so on. That's the typical thing. Okay. So from this process, we need a convexity which is somehow strange to me, but I cannot avoid it. So, okay, maybe I'm not an expert in this hyperbolic theory. Maybe it's crucial, but at this moment, I don't know. It's not clear to me. Anyway, okay. So let me show just a priori estimate. So you can testing u to the p minus 1 to the equation. Then, so one of the good points for the elliptic equation is we can structure of the this, which is the Laplacian of v could be transformed in terms of nothing but linear summations of u and v, which is minus v is also good terms. Okay, so integration by part, you just have that. So Laplace v is nothing but u, basically u minus v is okay. So the power of this is okay. We don't need the absolute value because u is always non-negative. U to the p plus 1. On the other hand, from the logistic part, oops, sorry. Okay, here. So then, because we multiply u to the p minus 1, so the power is p plus 1. So there are competition. This guy and this guy. This guy shows some aggregation effect. This guy is somehow, the minus sign. So we can compare this. So the p is larger and larger, then it converges to 1, by the way. So it's obvious that, basically, if mu is bigger than 1, then it's a good sign. If mu is less than 1, you could find the p, which is bigger than mu. So then, you see the left-hand side is a derivative of u to the p. This is the power is bigger than p, which is actually p plus 1. So then, the other part is also we have to control, but this side already implies that loss of infinite time, as long as this guy has a positive sign. Okay. Of course, we have to do many things. I mean, the estimate and so on. I mean, bounded domain case is maybe easier because Felder's inequality is easy, but the whole space we cannot use because the size of the domain is infinite. But then interpolation argument works, and so I'm not going to. Maybe you are interested in the Blowup case. So if mu is less than 1, then as I said, you could find the q so that this is positive, right? Okay. So bounded domain case, you always use the Helder's with this size of the omega. So it's a bit easy. Okay, this is bounded domain, global Eason's case, I think. Okay, sorry. Okay. Yes. Maybe in the whole space case, we have to interpolate this like this. So eventually, what you have is the following estimate. The point is, this is the power q, but this is q plus 1. So as long as initial data is large, then this shows a loss of infinite time. It's a kind of a typical OD types argument, right? Okay. So loss of infinite time. Okay. But I think the a priori is easy. Okay. So there are some technical calculations, but I don't think it's the main point. The main point is nothing but the comparison between the values of mu and p, okay? Okay, but this is kind of a priori estimate. Actually, we have to control the gradient of u. Otherwise, this is just nothing but just a priori estimate, but we are not sure the existence of such a solution. In other words, the all calculation may be meaningless because the formal calculation, we require that everything should be integrable, but the solutions are already second derivative. But is it rigorous or not, right? That's the question. So, again, it's again a priori estimate, but we need some control of the gradient of these two. If you have a parabolic elliptic, then easy because the appearance of Laplacian somehow, you can easy to control the, but hyperbolic case is not so easy. Okay, so one of the good point is this types of estimate. Why is that? As I said, actually the Winkler used that second derivative is just transformed in terms of summations of u and b, right? So basically this estimate is the second derivative. I mean, what I have in mind is f is the second derivative of v. Then the one-dimensional case is easily transformed, but in higher dimensions not easy because we have only control of Laplace, not the full second derivative. But these types of estimates are well known. At infinity in terms of kind of interpolations. Sobolev space. This is bigger than, okay, S is 1, then P is bigger than N. But typical estimate is at infinity is controlled by the Sobolev embeddings, right? I guess all of you are familiar with the Sobolev embedding. But slightly improved estimate is like you transform this in terms of BMO and Sobolev spaces, but the log. Okay, it was proven by Kojono and Taneuchi for the Navier-Stokes equation. I mean, one of the well-known property when it comes to regularity criteria for the Navier-Stokes, or maybe actually Euler equations, Vircato, Maida, but they improved kind of a gradient of the curve or something in terms of BMO spaces that where they use these types of estimate. I realized that this estimate is useful for our problem. So by using this, actually we have control of the gradient of u as long as solutions, I mean, for short time, okay, as long as the initial data is good. Let me show you the details. Okay, the equations, you know that this is a non-linear part, so you just expand it. By the way, still I have 10 minutes? Where is that? Yeah, okay. So, because I need a derivative estimate, you can take the derivative to the equations. So then, okay, for simplicity, let me write W, which is nothing but derivative. Then equation is like this. And then you multiply this, because I want some LP types of estimate. Then what you have is this. And this may be no problem because the Laplace B is always, you know, in terms of U and B. A priori, we have U is at infinity as long as mu is less than 1 or something. But the difficult part is this, second derivative. So here we use that, we take the L infinite. Okay, here still have this. Okay, next page maybe. Okay, so the a priori we need to control the at infinity estimate of second derivative v, which is not the Laplacian. If Laplacian, then it's easy, but not the Laplacian. Then we apply this estimate. One hand we split. It's kind of interpolations, but not the linear way. Actually, BMO times log Sobolev spaces. For this Sobolev spaces estimate, we may use the elliptic estimate. So this is like a third derivative of v, which can be a priori estimate in terms of a gradient of u, right? And on the other hand, BMO is a good spaces when it comes to singular integral. So the BMO is controlled by the BMO for the elliptic equation, which is controlled by at infinity. So the end up with, we have this estimate. So then, a priori is finite, and this is log times this. So from the ODE point of view, is double exponential growth, but never below of infinite time, a priori. Okay, that's the point. So somehow it's a bit complicated, but it's like a one case. So second derivative is controlled in such a way, so we succeed to prove the local equidistance. Okay, that's the idea. Okay, here is the process of the approximation. So as I said, we are considered a hyperbolic equation, but when it comes to constructions of such equations, such solutions, we have to add Laplacians. But the estimate we want is independent of epsilon, and then passing to the limit. Then we have a convergence. Of course, we need some convergences methods, but I think that's the typical part. But most difficult is that we need some uniform estimate, independent epsilon. That's why we are interested in a priori estimate at the beginning. Okay. Anyway, so why do we need the convexity here? You can, okay, by the way, I skipped the epsilon here. And if you testing this, by the way, for the approximating system, the local existence of solution is obvious because the Laplacians are there. Okay. Now, a priori, we testing this, then you have this, and also the boundary effect appears here, which is natural. I mean, we have a Neumann boundary, right? But we need some the gradient estimate. Then typically this is not zero. For the convex domain, actually, it has a sign. This is the derivative to the normal directions of the gradient of u. So why is convexity gives a sign? Computation maybe you can do, but also you need some time. But the reason is it has a sign is because the convexity has somehow the positivity of the Hessian. If you write the solution in terms of a graph, then actually Hessian is a sign, which is give the signs of this. Okay, so that's why it's pointwise that this is negative sign, which means because of the signs of negative, this is positive. So we can disregard this one. If it's not convexity, we do not know the effect of. But then we have to control this to the left hand side, but it's not okay because we want to estimate independent of epsilon. But if you have an influence of this, okay, suppose omega is arbitrary, smooth domain, then we have to control this boundary effect, but it's not obvious. But as I said again, this kind of difficulty appears only in the process of approximation, not in the a priori estimate. So at the beginning, I disregarded, but I got the comment from the referee, and we realized that okay, maybe convexity is needed. So we have to add something. Anyway, that's the technical part. Okay, this is a typical thing, and then when you have a sequence of solution, then because the other part is a priori estimate is working with independent of epsilon, then we passing to the limit is I think the typical part. Maybe I have to comment that why do you need the gradient estimate? Because strong convergence of the u square from the logistic terms, right? That's why we need some control of the gradient too. Otherwise, we don't have convergence, strong convergence. If linear is okay, but I think the u square, because we have a u square, so we need some strong convergence. That means we have the uniform bounds of gradient. That's why we need some, the gradient estimate. And so. Anyway, uniqueness is also possible when you establish the existence of solutions. Second part is maybe this more or less the same. So maybe if you don't mind, I'll skip. Same idea. So depending on the values of beta, plus of infinite time, or global existence, as long as beta is less than 1, subcritical case, the same procedure, same philosophy. Okay, approximation same. Okay, so the last part of this, my talk is about parabolic elliptic case. Again, I'm going to give the sketch of proof because technical, I don't spend the technical parts of this computation. The main point is that in the case the values are exactly mu is n minus 2 divided by n, then the p0, which is defined by 1 divided by 1 minus mu, it turns out n divided by 2. So a priori, we can do LP types estimate because we have a Laplacian there, so we have this. Okay, and then it turns out this guy has a good sign, which means non-positive. So I think that this estimate is available a priori. But it's not enough. Actually, we have to have at infinite types of estimate, which means the restrictions of P, which is less or equal to P0, is not enough. Actually, we need more LP types estimate. So how can we improve? For these numbers, it's fine, but we need some more higher integrability, which means P is bigger than P0. Okay. So what I realized is that now, we choose a P slightly bigger than P0. So as long as P is less or equal to P0 is fine, we have estimate. But P is bigger than P0, then it's a kind of a critical, super critical case. But what I realized is that this is number, which of course bad sign, positive. But depending on choice of P, this value could be as small as you want. That's the one thing you keep in mind. And then I realized that again I tried to LP types estimate, which it turns out this coefficient appears in the right hand side, which is again bad. Positive parts. Now, Now, when it comes to this estimate, because of kind of a critical case, so I have this kind of estimate, but which is already finite. P0, which is n divided by 2, this is finite. But the fact is that this coefficient is very tiny. Of course, depending on choice, but at the beginning, I choose a P, which is slightly bigger than P0, but quite less than, delta is small. So, end up with this coefficient is small, and then the size of this is comparable to the left, which means this guy is bad, but could be observed to the left. So then the remaining thing is okay. Okay, that's the idea. So, in other words, we slightly improve the integrability of this U up to P0 plus delta. Once you have that, and then it turns out subcritical case. Now we can using this information. Now the solutions is not in up to L_P0, actually more than that, slightly bigger than P0 plus delta. Then again we can use this information. Then again repeating this estimate. Then actually estimate we can improve it's like a bootstrapping argument. So improve the integrability P again and again. So because it's a critical case, it works. I tried the same kind of argument for the subcritical case, but then it was because the right hand side doesn't match. So even if you take the small coefficient, but then the right hand side we require more regularity than the left, so it doesn't work. Okay, and that works only in the critical case. So the other part is I think the technical part in the computations. So let me stop here and then thank you for your attention.